So correlation and the graphical representation, when we're looking at correlation, we usually use scatter plots. So it's when we have bivariate data, we're comparing two sets of data. Here is a scatter plot. Now this is actual data, I forget which year it was, probably 2019. I think I wrote these in 2020. So from the year 11 yearly exam results of that particular year, comparing students' extension maths result with their 2-unit maths result and how that compares. You would hope there would be some sort of relationship between the two, and you can see you've got this nice clump and it looks like it's linear, sort of what you would hope to expect. Interestingly, when you compare the English extension results with the English 2-unit results, not quite as clumped together and not quite as linear. Then what the heck, let's compare the maths extension results. And remember, these are only people that did both the exams, of course, because you need the data. So there's the maths extension versus the English extension. There's maths extension versus business studies. And one more, maths extension versus PDHPE, that particular year. Interesting. Now, correlation then is the strength of this scatter. So how strongly the relationship is, and it should go between -1 and 1. 1 being a perfect correlation, -1 being an absolutely hopeless one. It would be reversed. It would be a perfect correlation, but in the negative way. So if one's high, the other would be low, and vice versa. So what were the correlations for these? Well, for the first one, that ended up being 0.81, which we would consider a strong correlation, and we certainly would hope that would be true when you're comparing your maths extension with your maths. The English one was 0.49. That falls in the category of what we would call a moderate correlation. So there's still a correlation there. Maths extension versus English extension, 0.23. That's a weak correlation. The business studies one is 0.01. So they say, well, there's virtually no correlation. Yeah, okay, well, there's no reason why there should be, I suppose. I mean, they're two totally different subjects. The PDH one actually ended up with a negative correlation. So that one's interesting. So, but again, it's a very weak one. So again, there's no reason why they would correlate. They get two totally different subjects. So as with any graph, we usually put the independent variable on the horizontal axis and the dependent variable on the vertical axis. Now, when you're doing something like correlation, it may not be obvious which one's independent, which one's dependent, because in the last examples I was looking at, it was just two subjects. It's not one depends on the other, so it probably doesn't matter which one you put on each of the axes. Now we're going to be concerned with linear correlation. We're looking for linear ones, but it doesn't have to be linear. That would be a very strong exponential correlation if you saw the data fall in that sort of pattern. That would be a strong inverse correlation. Sort of got that hyperbolic shape. It could, if there was some really weird data, you might get a strong quadratic correlation. Goodness knows what that would be, but you could get it. So we're concerned with linear correlation. And the reason why is this thing called a line of best fit. Because clearly, if it lies in a nice, perfect linear correlation, we could draw a perfect straight line through all the data. We could come up with an equation from it. And the idea of the equation is, of course, we can then make predictions. When you look at it, though, you need to identify multiple points, because you might be placing one point down, but there might be 3 pieces of data that have exactly the same information. And so you normally would say maybe circle it to indicate, hang on, there's more than one point here. And if there's more than 2, you might actually write the number there. So that when you're drawing your line of best fit, you know actually, there's more data going towards this point. Let's have a look at our maths versus maths extension. Now by eye, of course, is the easiest way to draw a line of best fit. There's my one. I thought, that looks pretty good. What you're trying to do, I guess, is trying to keep an even amount on either side, but you're trying to balance it. So that's where I put it by eye. Assuming this data is reliable, then you can go and make your predictions. There's 2 different types of predictions. There's one called interpolation. So you might have heard that expression, I'm going to interpolate the information. Interpolation is where you're making a prediction within your range of data. So for this one here, the example I used is, well, I could predict here that someone that scored 40% in extension probably scored 70% in the 2-unit paper. Now I can do that because it's within the range of my data. So that's what you call interpolation. The other one, which you probably have heard of, is extrapolation. I'm going to extrapolate the results. And that's when you make predictions which is outside of the gathered data. So I'm going to extrapolate it and make a prediction. So theoretically, if someone scored 20% in mass extension, then I would have expected them to get 60% in the 2-unit paper. So that would be extrapolation. I don't know how far it becomes valid because, you know, someone got 0 in extension. Oh, but it's okay, they got 50% in 2-unit. Don't know if that realistically would happen, but the data would suggest that that's what would happen in this case. But there's this other thing called causation. So correlation versus causation. And this is the biggest mistake people make with statistics, thinking they're the same thing. Just because we have a correlation doesn't mean it's true. What correlation is used for is you look at the data. If there is a good correlation, that gives you reason to, okay, maybe this is something we should investigate further. So it allows you to pick up possible relationships and find out what should we be investigating, what should we be researching to see if this is valid. And let me show you some examples here. Now, during summer, people get hay fever. There's also a lot of pollen in the air in summer. In fact, there is a strong correlation between the presence of pollen and hay fever. So that's the correlation there. So the suggestion is that, well, pollen must cause hay fever. So that's the causation. Is it true? Maybe, but it actually is true. They had then gone and done studies on that and found, yeah, that makes sense. It does happen. But then look at this one. During summer, the sale of ice cream increases, but so does death by drowning. In fact, there's a strong correlation between ice cream sales and death by drowning. Well, therefore, ice cream causes drowning. Now, that is what you would conclude from this. That's the causation of it. Well, I hope you agree with me that that's actually not a sensible correlation. They're just things that happen to happen more in summer. Yeah. So that's the difference between correlation and causation. So correlation does not mean causation. Correlation just says, hey, investigate this further. Okay, so 15G on correlation.